Okay, everyone, let's get started. So today I'm going to deliver a lecture. Hopefully it won't take the whole class, but it might. I want to finish this Verilog lecture, or at least get to the point where you can start Lab 2. Lab 2, you'll start using Verilog and the FPGAs, okay? So last time I introduced SystemVerilog, and I talked about how there's three different ways to represent hardware designs. There's behavioral, which is kind of like the mathematical description of what the hardware is doing. Then there's the structural, which is generally like a schematic or a block diagram. And then the physical is where you're actually allocating nodes in the structural design to physical hardware. So going from behavioral to structural and structural down to physical is the job of the CAD tools we're using. You don't actually have to worry about that. You just have to understand what's going on. Like when you hit the run button in Quartus, it's taking your Verilog code, it's going to synthesize it into a net list, which looks like that, and then it's going to take that net list. Net list is just a schematic text version, textual representation of a graph, which represents a schematic. And then it's going to place each one of these logical components onto physical slots on the FPGA, and then it's going to connect them through the wiring, the fabric, the interconnect, right? And that takes a while. You're going to spend a lot of time waiting for it to do that, but you don't have to worry about how that works. Luckily, that process is all automated, okay? So, so we're going to be using Verilog, or SystemVerilog actually. And Verilog is designed around the concept of a module, and modules are there in order to allow you to express hierarchy. So you can have a design that instantiates modules that also instantiates modules within them, and so on and so forth. So this is a way that you can describe a very complex design, but if you look at any one file, any one design, it looks rather simple, right? And then modules also allow you to express regularity. So you can design a module that you can kind of stamp out multiple times. You can instance it multiple times. So you want to try to build modules that are as reusable as possible, right? Okay, and then we talked a little bit about logic circuits in general, and that logic circuits have inputs, outputs, a functional specification, and a timing specification. And so when you design in SystemVerilog, the module is essentially a logic circuit, right? So on the first line of the module, you define your inputs and outputs, and then inside the module body is where you have the functional specification, and then the timing specification is something that you would give to the CAD tools. So when it does the place and route process, it achieves the timing spec that you give it, which is usually in the form of a clock speed. Clock cycle speed. And so it has to, the job of the CAD tools is to place and route it in a way where the critical path delay, or the worst case delay in the circuit, is fits within a clock cycle that you specify. So if you tell the place and route tool, if you give it a tighter timing specification, you tell it you want it to achieve a higher clock rate, it's going to take longer for it to compile, and in some cases it won't be able to compile it at all. In this class, we're using a very easy to achieve timing spec, which is 50 megahertz. So you're going to do some designs, and we're going to tell the tool, you gotta place and route this in a way that makes it, you got to guarantee me that that'll work at 50 megahertz, regardless of the temperature, what temperature the room is I'm running the FPGA in, because that affects the performance, the delay of the logic, and regardless of any kind of design, manufacturing variations on the chips. You got to achieve 50 megahertz, and that usually ends up being, for this class in that FPGA technology, not too bad. So, it's usually not too difficult. You're probably never going to see a case where the tools fail to achieve that timing spec. Now, if you want to get crazy and say, hey, I think I ought to be able to run my CPU at 200 megahertz, well, then you can tell Quartus to achieve 200 megahertz, in which case it's going to take much longer to compile. And it may not be able to do it. You may have to go in and deepen your pipeline. You may have to go into your code and design your code so you have a shorter logic path in each cycle from register to register. But we'll talk more about that at the end of the semester. So for this project, 50 megahertz, you generally don't have to worry about it. Okay, so we talked about this combinational and sequential logic. You should have hopefully covered that in 211. Combinational logic is where the outputs are just a function of the inputs, whereas sequential logic has memory, and so the outputs are a function of the inputs in the input history, right? And so I bring that up because I'm going to refer back to combinational and sequential logic later. We talked about timing diagrams, right? We got to this point, right? I'm sorry, not timing diagrams, schematics. So basically the projects in this class, or at least lab 3 and 4, where you design the CPU, will just essentially involve you translating schematics that I give to you for the RISC-V CPU, and you're going to just translate them to SystemVerilog, basically. So it's important that you be able to read schematics, right? So schematics have, if you have a very low level schematic, you might have a schematic having logic gates in it, like the kind that you saw in 211. But as you get higher in the design hierarchy, the schematics are going to be represented as block diagrams, where everything in the schematic is just a block, because there aren't symbols defined for components except at the very lowest level, the basic logic components, right? The basic digital logic building blocks, like the gates, muxes, decoders, flip-flops, those have standard IEEE symbols associated with them. But as you go higher in the design hierarchy and you start putting a register file down, or a floating point functional unit, or a control unit, there's no symbols for that. So mostly it's just blocks. And generally speaking, those blocks will have inputs on the left and outputs on the right. And then you're going to connect those blocks together with wires. And again, in Verilog, you don't actually draw, you don't make any drawings. You're defining all these connections in text using structural Verilog. But when you represent it in a design, it's often done graphically, right? So again, you have to be comfortable with looking at a block diagram and then being able to write it in SystemVerilog, structural Verilog, right? Okay, so when you look at these diagrams, you're going to have a lot of wires. It's very difficult to organize the blocks to where you don't have crossings of wires. So when you do have a cross of wire, if there's no dot there, they're generally assumed not to be connected. If there's a dot, they are connected. But then if you have a T-junction like this, the assumption is that they are connected, because why else would that exist unless you intended to connect those? If you do have a T-junction, by the way, this is going to be a fan-out. So remember that when you have connections like this, there's basically 3 points on this connection. You can only have one driver for that net, that wire, right? So only one logic circuit, which could be a module that you instanced, or it could be some behavior that you put in, like an assign statement. But only one thing can actually put a logic value on this wire. So because there's 3 points on this thing, probably one thing is driving it, and then there are 2 things that are going to inputs on other parts of your diagram. Does it make sense? Okay, so just keep that in mind. If you double drive a wire, you're going to see X contention in the simulator. And if you try to synthesize it, I think you'll get an error, right? But then if somehow you do get a design where you're legit double driving a wire, that will generally physically damage the device, because you're going to have a short circuit potentially if you've got one circuit trying to set a logic 1 to that wire, another one trying to set logic 0. Okay, and so we talked about contention. So by the way, SystemVerilog is called 4-state logic. So when you declare a value as logic, it can be a single bit or multiple bits. Right? I just had barely gotten to the multi-bit logic last lecture. But each one of those bits is actually not a bit, it's a logic value. And in Verilog, that logic value can be 0 or 1, but also can be X, which means unclear what it is. X is used for don't cares. If you set a value in your code as X, it means don't care. They should have used something different for that. In VHDL, they do use something different. In VHDL, it's a hyphen as a don't care, but for some reason, we don't have the hyphen value, we just have an X. So if you set a value as X, that means don't care. But if you see a value set as X and you didn't set it that way, that means it's either undefined because it's an uninitialized memory, or most often is the case in this class, it's contention, which means that you've accidentally double driven a signal, right? So that's X, and then there's Z, which stands for high impedance, which is where this is intended for use with a tri-state buffer, where you can electronically disconnect a signal for the purpose of creating a shared bus, right? And so we're not going to ever use this in the class, but the other thing is if you have an input, I think I showed this last class, Z also shows up if you have an input into a module and you simulate that module, but you don't set the input with a stimulus of some kind, like you don't set a test input on there, you'll see Z for that too, right? So Z can be, set by you in your design, or it could just be in there as a consequence of you forgetting to set an input, right? Does it make sense? So that's why those are 4 states. Now there's actually, Verilog is 4-state. I think SystemVerilog introduced a few other values. You have a strong one and a weak one. But we're not going to use those in this class. But just in case you happen to see in the simulator, you might see a strong one, ST1. Just consider that, logic 1. Okay. Another thing too that I want to mention is we use like I mentioned, we're using ModelSim, or actually QuestaSim, which is an industrial strength simulator. It's made by a company called, was originally made by a company called Rhinosoft, but then that Rhinosoft was purchased by Mentor. And then Mentor was purchased by Siemens, so it's actually come from a company called Siemens. But it is considered the kind of the industry standard simulator, but it's not free. It's actually quite expensive. We get a good deal on it here because we're a university and they want us to teach it to you guys. But if you have a company and you buy it, it's expensive because it's also kind of it's designed for specific sectors that make hardware. There are some free ones. But there are limitations. There's 2 in Linux. One's called Icarus Verilog, which only supports Verilog and not SystemVerilog. And there's another one called Verilator. And both of those things, instead of being a simulation engine like ModelSim is, those ones actually convert Verilog to an executable file that you can just run in Linux. So basically, it takes the behavior that you specify in the Verilog, and it kind of merges in a simulation engine with it into a single executable. There are limitations though, because in SystemVerilog, there's only 2-state logic. So you don't get the contention and you don't get the high impedance in Verilator, right? Which is why we don't use it in this class, because Verilator is not a great way to do debugging and test because you don't get those 2 extra logic values, right? And I think they do that to make it faster. And I think Icarus Verilog may also have the same limitation as well, but we never got to even try it because it doesn't even support SystemVerilog. And we support SystemVerilog in this class because it fixes a lot of the really annoying things about Verilog, and it's kind of the new industry standard, and the textbook switched to SystemVerilog. So that's the reason we switched. Okay, everyone with me? So there's not a lot of good free options, basically. We're not using ModelSim because we're snobby. It's just there's really no better kind of open source solution to that I know of anyway. All right, so I talked briefly about the history of HDLs. The 2 most common ones are VHDL and Verilog. We use Verilog. It's more commonly used in industry. And then I also talked about, I showed some examples. In this case, we have a Verilog module, and this is purely behavioral Verilog code because it uses what's called the continuous assignment statement. In VHDL, it's called the concurrent assignment statement, but basically it's the same thing. It's essentially a way to assign a signal, which is basically creating a logic circuit that's driving this signal Y, because this Y is on the left-hand side, and thus that's the output, and that's the driver is connected to that. So it's creating a circuit that's wiring this wire, Y, directly to a transistor network that would potentially pull it up to VDD or pull it down to ground, right? And then we just have some Boolean logic here, and you should recognize it's the same syntax essentially that you use in C and Java. Notice though that we use single ampersand, which is a bitwise AND operation as opposed to a logical and the tilde is a bitwise complement, and the single bar is a bitwise OR. So we create this Boolean logic, and then we can simulate it using ModelSim or some other discrete event simulator. The results here are presented as a waveform, and in this case, A, B, and C, this circuit is only driving Y. So who's driving A, B, and C? Presumably a test bench, that wraps around this, or you can set these values directly from the simulator using a language called Tcl. In this class, we're going to focus on test benches, which is where you use a Verilog module in order to set the inputs for another Verilog module that's inside of it. And then the outermost Verilog module, the test bench, can also verify the outputs of the one inside. So the one inside is called the design under test. So this would be like a design under test if we were testing it, and we can wrap it into a test bench, which the test bench would then be responsible for setting these A, B, and C inputs and also verifying Y. Now you might say, well, wait a minute, why not just check it? Why not just read it? Well, you can't always do that. This is simple, so we can exhaustively test this, in which case we get a waveform that is essentially the horizontal form of a truth table, essentially, because A, B, and C just count from 0 to 7, and we look at the corresponding values of Y. Right? And when I say 0 to 7, I'm talking about the numerical representation of these 3 bits if I assume these 3 bits formed a number, right? A binary number, right? In which case, in this case, C would be the least significant bit because it goes high first, right? So there's 001, 101, 011, 100, etc. Okay? All right. Okay, then when you synthesize that, the synthesizer minimizes the circuit, so even though it appears that I ought to have a 3-input OR gate and 3 3-input AND gates, I don't have those for some reason because it minimized it. It simplified the circuit into an equivalent form. Okay, SystemVerilog, case sensitive, comments match C and C++ and Java. White space is ignored, and then we talked about structural. So this is an example of a structural design where I have a top-level design, and I'll say that term I use a lot because whenever you simulate or synthesize, you always start with the top-level design, which is the root of the design hierarchy. It is the most abstract, module, and then inside that module you have other modules. So the top-level design is called NAND 3. Inside NAND 3, I instance an AND gate and an inverter. And then the thing that's really confusing is that I have one wire inside the NAND called N1. It's declared locally. However, because that N1 is what connects the Y output of this guy and the A input of this guy, I now have 3 different names for the same wire. Right? It's called Y, it's called N1, it's called A. It depends on where you're looking at it, what the scope is that you're looking at it in, okay? So keep that in mind. Now, ModelSim will actually show, whenever you simulate ModelSim, it will show you the design hierarchy on the left-hand side. So you can drill down by using a little tree, like a little Windows registry sort of thing, if you guys know what that is. You hit the plus sign and it expands out and you can drill down, right? But if I did that and I put Y and N1 both in my waveform, they would be locked. They would always be the same. I could change N1, which would change this Y, or I could change this Y and it would change N1. It's the same wire, they just have different names because of the way they're connected through the hierarchy, okay? Okay, so then I think the last thing I got to on Monday was these multi-bit. This is a weird syntax thing with Verilog. It's really annoying for 2 reasons. One, the array indices are put before the variable name, which is like no other language that's ever been written. There's no other programming language that does that, that I've ever seen anyway, where the array size is placed before the name, right? Usually it's after the name. But the nice thing about that is that because it is before the name, I now have A and B that are both input logic 4 bits, right? That makes sense? So basically the array size is kind of combined with the type name as opposed to the way C and C++ and Java do it, where they put it after the name, in which case it would be harder to do this kind of trick, right? The other thing is we put 3:0 instead of just 4. That makes no sense to me. That's totally bizarre. Don't know why they do that. I also mentioned that if you were to put 0:3, it would make no difference. I don't know why they do it that way, but basically if you have an n-bit signal, you have to write n-1:0. All right? It's just supposed to represent the 2 extreme ends of the index range, right? Now, if this were VHDL, by the way, it works the same way, except you would have to type out array, and you would have to type the word range, and then you would have to put 3:0, which is ridiculously verbose. but that's how VHDL is. It's all spelled out, but it's equivalent to doing that. Oh, and instead of logic in VHDL, it's called standard underscore logic underscore vector. So everything is super long and drawn out in VHDL, but it's equivalent to what's in Verilog. Okay, and then another very common operator that's used in Verilog is the ternary operator. And this operator is actually available in Java and C, but you might have not ever used it because it's less commonly used in programming languages, but it's very commonly used in HDL because it creates a multiplexer. So basically what happens here is that the ternary operator has three parts in it. The first part is a condition that's tested, right? The second part is what happens if that what the expression evaluates to if the condition is true. And the last part is what the expression evaluates if the condition is false. So that very naturally maps into a multiplexer where the condition is the select on the multiplexer, and then the middle input here is the one input on the multiplexer, and then the second one is the 0 input on the multiplexer. So in your CPU design, you're going to have a lot of multiplexers because multiplexers are fundamentally how you steer data around to create data paths, right? It's also how you multiplex inputs. So for example, the register file has an input called data in. That's the data that you write to the register. But that data could come from the ALU, or it could come from the memory, right? Or it could come from maybe a coprocessor, if you want to transfer a coprocessor register into a register. There's various places you can get data to put in the register file, but there's only one port, there's only one write port on the register file. So the way you deal with that is with a multiplexer, which allows you to select who goes in, which source is routed into the data input on the register file. And hopefully you guys saw some examples of that in 212, right? So multiplexers show up a lot in your design, and they're nice because you can just write essentially one expression, which the synthesizer will then interpret as being a multiplexer. So even if you have a structural design where you have a register file and a control unit and an ALU and all these big abstract blocks, you still will mix in these little multiplexers will get kind of mixed into the structural code just to take care of fan-ins where you have, because remember, you can only each signal can only be driven by one driver, so if you need to be able to get multiple sources into a place, you got to use a multiplexer for that. That's how fan-ins are done, is with multiplexers, right? The other thing you commonly will put in with little snippets of code are flip-flops / registers. So multiplexers and registers are the most common little bits of behavioral code that you kind of mix in with structural code, right? If that makes sense. Remember, structural code is just instancing a module and connecting it to something else, okay? So in this case, what is this, by the way? This is a 2-to-1 multiplexer where the inputs and the outputs are 4 bits each, right? Because they're declared as 3:1. And so when I simulate this, in the simulation, I've got D0 and D1 are the two inputs which are changing, and I've got S which is changing. And so in order to figure out why, I have to look at S. So because S is 1, that means I'm selecting input 1. Input 1 is D1. So D1 is basically getting copied to the output of the multiplexer here, right? But if I go one cycle before that, you can see that the multiplexer is outputting 0, 0, 1 because the select is 0 and input 0 is 0, 0, 1, right? So like I said, this ternary operator, and you can nest these too, which is nice if you want to create a more than 2-to-1 multiplexer. You can create nested versions of the ternary operator. Okay, so then we have, one other thing I want to mention too. You might say, wait a second, hold up. Why not use an if statement for this? This is just an if condition, right? Like if the select is 0, then the output should be input 0, right? Why not use an if statement? Well, you actually, in SystemVerilog, you can only use an if statement if it's inside the context of another construct called an always statement, which I'll talk about soon. So you can't just put an if statement inside here, right? You can put an if statement in, but only if it's inside of another block called an always block, and I'll talk about that in just a moment. Okay, so I think I covered this. These are internal signals, just another example. This table is something I refer to often. This is basically the list of the operators in Verilog and their precedence. And so this is highest precedence to lowest precedence. Notice the ternary operator has the lowest precedence of anything. So you don't have to worry about putting things in the ternary operator in parentheses because it's the lowest precedence. So we have the not, which is this is the bitwise complement not operation. Then we have mult, div, and mod. So these ones you generally are not going to ever use in Verilog code that you intend to synthesize, because whenever you're building code that has a multiplier, you're usually going to define that multiplier at a lower abstraction. You don't want to give the synthesizer the ability to generate its own multiplier architecture, because there's this huge design space for multipliers. Usually multipliers will either be oftentimes you'll have like an IP block, a module that you use for a multiplier. But then again, I mean, remember that Verilog can also be used for in a way that doesn't intend to convert to hardware, like if you're building a test bench, right? A testing infrastructure. Then we have add and subtract, and then there's two versions of shift. There's a shift, a regular shift, and then there's a type of shift that's not available in C++ and C and Java, and that's the less than, and greater than form of the shift. And this is for doing arithmetic shifts, right? You guys remember logical versus arithmetic? So when you do a logical shift to the right, you always shift zeros in, right? But if you do an arithmetic shift to the right, you shift in the sign bit. Remember that? You guys remember that? These are not available in C and Java. Why? Well, in C and Java, the decision of whether you're doing a logical or a arithmetic shift is determined by the data type, the variable declaration of the thing you're shifting, right? So if you declare a variable as unsigned and you shift it in Java, it's going to do an unsigned logical shift, right? But if you declare a variable as assigned, like an integer, and you shift, it'll be a signed shift, right? But in Verilog, we don't have signed and unsigned. There's logic, right? So as a result, we need to be able to differentiate those by these different operators. Now, there is actually a way you can typecast a variable as signed, but by default, the logics are unsigned. And you might say, well, wait a minute, what's the point then of doing, why have a left arithmetic shift? That makes no sense. It does if you shift by a negative amount, in which case the left shift becomes a right shift. But anyway, then we have comparison, less than, equal, and then there's also equal and not equal. Now there is a variant of, this is not an exhaustive list, by the way, but there is a variant of the, I thought I had it in here, I guess I forgot. There is a variant of the equal operator, equal. There's equal, and there's equal, right? There's three equals. And likewise, there's not equal and not equal. The difference is, it has to do with the four-state logic. Remember that in Verilog, there's four states, but in reality, there's only two states, 1 and 0, right? So if you use a equal, then it's assuming that you're just concerned about real binary values, 0 and 1, right? But if you're writing a test bench and you want to compare to, say, a don't care, an X, right? Then you want to use the equal, right? Make sense? But if you compare, like inside of, if you use X equal X, that will be false. You might, no, X is equal to X. Well, no, but X doesn't really exist in real life. It's just a concept. So equal is for hardware, synthesizable code you want to put in hardware, and then you can use the equal when you write a test bench, because then it allows you to compare to non-existent values like X and Z. Okay? Okay, then we have and. Also, check this out. There's a NAND operator. This is not in Java or C++. Tilde ampersand, right? That's a Verilog exclusive thing. Likewise, you have XNOR, tilde, caret operator. So yeah, anyway, so those are operators. Most of those you're familiar with. Okay, and then the other thing too is that another consequence of the logic type not being standard data types like you have, in Java and C, you've got int and short and char, right? Which have these predefined widths, number of bits. With logic, there's really no, default bit width, right? There actually is in Verilog, the default is 32, but when you're doing Verilog design, you don't very commonly use 32-bit values. You might have a 1-bit or a 2-bit or a 3-bit or 5-bit or 9-bit value, right? So the problem is that if you have a scalar constant like 3, for instance, the compiler, it doesn't really know how to interpret that, right? How many bits are you talking? You say 3, but how many bits is that 3? So, and also, what about the base? Obviously in C and Java, you can say 0x to represent hexadecimal, and I think 0b is binary, right? But Verilog, it's a little bit different. So generally, whenever you have a constant, you specify the bit width, right? And then you put an apostrophe, and then you put B, O, or D, or H. B, binary, O, octal, H, hex. D, decimal. There's D and B. Decimal, binary, D and B, right? So for example, if you put 8 apostrophe B11, that's actually 11 in binary, which is 3 in decimal, and you're putting it in 8 bits, which means that there's going to be 6 leading zeros and 1, right? So it's good practice to always specify, whenever you have like something like this, which you may have like if for a multiplexer, like, you're going to say if the select is 0, if the select is 1, if the select is 2, and you should have the bit width and the base there for those. A lot of students in this class forget to do that, and then there's a warning message that gets sometimes you don't see it because it scrolls by with a lot of messages that are printed when you synthesize and simulate. But it's good practice to use this format. And also, notice we have an underscore here in this number. This is actually a nice feature because the underscore allows you to take a constant and actually split it into fields that you can read, but that underscore actually has no impact on the value, right? So it's just for decoration purposes, it's just for readability. But it's very common if you have a binary number that's that logically split into multiple parts, you can separate them with underscores. But it's optional. Okay? Okay, all right, and then another thing that's different is how you do bit manipulations. So it's very common that you want to take multiple values and concatenate them, right? So when you do that, it's very easy. You use the curly brace. Now remember that in Verilog, the curly braces are not used to define the beginning and end of a block like they are in C and Java, right? We don't have those. The curly braces are specifically for these bit manipulation things. So in this case, I'm assigning a value y, and I want to form the value of y by concatenating together several things. So in this case, I'm taking the value a, and I'm indexing it 2 down to 1, which is taking bits 2 and 1. We used to call this bit slicing, where you take bits out of a vector, of a logic vector, logic vectors, VHDL, of an array of bits, multi-bit logic value. So this is going to take 2 bits out of A, and then it's going to concatenate. Now this is a little weird. This is a duplication operator. So this is where you take bit 0 of the B value, and I want to put 3 copies of it. So in order to do that, you have to have both the inner and the outer curly braces here. So the inner curly braces is going around the thing you want to duplicate, which itself could be a concatenation of multiple things. But then the outer braces have to go around the thing you're duplicating and the duplication factor, right? So this just creates, again, it copies. Now you might say, when in the world would I ever use that? Well, sign extension, for example. So whenever you sign extend a value, like for example, RISC-V uses a 12-bit immediate value in its I-type instruction. You might say, wait a minute, I thought it was a 16-bit immediate. Well, in MIPS is 16-bit. RISC-V dropped the immediate field to 12 bits for some reason. I don't know why they did that. Seems odd to me, but there's a 12-bit immediate. So if you say add I in RISC-V, you only got 12 bits to put the immediate. Of course, you can combine it with another instruction if you want more bits, but in one instruction, you can only have a 12-bit immediate. That 12-bit immediate, if it's used in the context of a signed operation like add, the 12 bits is going to have to be sign extended to 32 bits, and the way you do that sign extend is you duplicate the sign bit 20 times. 20 times, yeah, 20 sign bits and 12 immediate bits. You guys with me? So that's a common use of that duplication thing. And then I mixed in this binary value, 6 bits, binary 100010, right? So I'm taking all these things and I'm going to combine them together and put that into Y. Now the cool thing about this concatenation is you can actually use this concatenation on the left-hand side of the assignment statement too. So in this case, I actually taking Y and I'm going to reformat it into these two fields. So I'm going to take 3 bits of Y and put them into A bits 2 down to 1. And the least significant bit of Y is going to go into B0. This is pretty cool, right? I think it's kind of neat you can do that. Of course, you could also do that with just 2 assign statements. You could split this into 2 assign statements, in which case you could assign this part in one statement, assign that part in another statement, and then of course you'd have to slice into Y on the right-hand side. But that's just a more a way to do it in one statement. Okay, so here's actually an example of a sign extension. So this is actually a 16-bit sign extension. So this is not the same code you're going to use. This is from the MIPS days. But B is a 16-bit value, and I'm going to take B bit 15, which is the sign bit of a 16-bit value, and I'm going to copy it 16 times and use that to fill in the other 16 bits by converting this 16-bit value into a 32-bit value, right? Okay. Okay, so it's an example of using 2 muxes together to create a wider mux. And then there's this reduction operator. This is another cool feature that you might have seen. So you can take A, if A is a vector, in this case 8 bits. Say I want to take the 8 bits that comprise A, and I want to feed them into an 8-input AND gate. I just want to AND together all the bits of A to go from 8 bits to 1. It's called a reduction because I'm going from 8 bits to 1 bit, because I'm going to feed all the bits of A into basically a big AND gate. You can use this format, this syntax rather, which is ampersand before A. That'll do a reduction. So that'll take the A value and just feed all the bits into an AND gate and give you one output. So the only reductions that are available in Verilog are AND, OR, AND, NAND, OR, NOR, XOR, and XNOR. There might be some more in SystemVerilog now. I think these are the ones in Verilog, but that may also apply to SystemVerilog. Okay, any questions? Everyone okay so far? Okay, so I showed an example of simulation, and I'm going to come back up. I might do another demo here. I just want to review that real quick. We have a simulator called, I'm calling it Model Sim. It used to be called Model Sim. Now the new name is QuestaSim. I mentioned QuestaSim. QuestaSim and Model Sim are the same thing. I don't know why they changed it. But when you initially open it, you can just run the vsim command. You don't have to do anything to set it up. It should just come up. You just have to open a terminal and run vsim, and you'll get this screen initially, or something that looks like it. You'll notice that there's a library tab, and there's a bunch of stuff in the library. This library is actually, these are simulation models of primitives, FPGA primitives. So an FPGA is this kind of reconfigurable fabric, but it's physically comprised of primitive circuits. And I mentioned to you LUTs are kind of the most common one. A LUT is a reprogrammable logic gate. But there's also things like multipliers and BRAMs and IO buffers. And there's a bunch of, and there's a phase lock loop. You know, the clock thing, it changes the clock frequency and phase. right, of a reference clock. There's a bunch of stuff on the FPGA. And this, what you're seeing here are models. And the reason why there's so many is that every FPGA technology, every FPGA generation has a different set of models that allow ModelSim to, instead of just running SystemVerilog, you can instance a primitive. In other words, I want to create a LUT and just model and have ModelSim, behave, know how that LUT behaves. We're not actually going to use any of those, so don't worry about it. Just ignore that. The one that will be added here for you will be at the very top. It's going to be called work. And that's the library where all your designs are going to get put into whenever you compile SystemVerilog code with the vlog command. Okay. Now you can compile in here too. So there's a GUI. You'll notice that there is a compile menu here. So you can compile designs through the GUI, or you can compile them through this little command line interface, or you can compile them in a shell. I usually just compile them in a shell. I type vlog space star.sv, and that just compiles all my SystemVerilog files in the directory. And it puts them in the work directory. The work directory will then pop up as a work library, assuming, of course, that you launch ModelSim from the same directory that you compiled the files in, right? If you didn't, it's no problem. You can just use the cd command down here to go to that directory, in which case the work will show up. The work library will show up. Okay, and then, so this is the compile dialog. So this is compiling through the GUI. And then when you want to start the simulation, you can actually just type vsim inside the command line window with the top level module as the argument. So vsim space CPU, right? Or vsim space test bench. Or you could do it through the GUI. This is the way the GUI set up. You just go to simulation, start simulation. Now, one of the things that they added in ModelSim in the last few years is this thing that's kind of annoying. They started using this optimization by default, because remember that this QuestaSim is intended for industrial designs. Like this is intended for like Intel to be using, right? And so the idea with ModelSim is that they're always trying to make it faster for simulating large scale designs. But the problem is in this class, all our designs are small. But one of the things they did to speed it up is by default, they turned off visibility for internal signals. So like you'll simulate your top level design and then you drill into it and you want to plot your signals and you don't see them, they're gone. Because they turned it off by default. But you can fix that. There's just an option. When you click optimization options, you could tell it to apply full visibility to all modules, which they call full debug mode. And this will not impact the performance because our designs in this class are so small, it has no problem with, logging all the signals, right? Or having all the signals available for logging purposes, right? When I say logging, I mean plotting, printing, right? You guys with me? Okay. I think I showed that last lecture. And then, you can bring up a wave window and then, now just to be clear, in ModelSim, you basically get two versions of that GUI depending on if you're in simulation mode or not. If you start it up without typing the top level module, like if you just type vsim, it goes into a mode where it's like dead, right? It's not simulating anything. It won't actually go into this mode where you can look at the waveform and stuff until you tell it to start simulating, right? On the other hand, you can start simulating right away if you type vsim space top, right? Or whatever your top level module, and then it'll come up in simulation mode, right? But sometimes you might start it and you're like, why is it not doing anything? It's not letting me do anything. I can't open waves. I don't see this, design hierarchy. It's because it's not in simulation. It's not actively simulating, right? Okay. And then this is the design structure. This is what I was talking about with the design hierarchy. So this is pretty cool. In this case, test bench is my top level module. And inside test bench, I have something called my adder, which is obviously the design under test that I'm testing. But then inside of my adder, I have three registers. I have input register A, input register B, and output register S, which is the sum. So I have registers holding the two inputs and a register holding the output. And then I have my adder, and inside my adder, I generated, in this case, 9-bit adders. So I created a 9-bit adder inside that adder, I created 9 single-bit full adders, right? So that's what's going on here. And then if you click on any of these, you'll see the signals inside that level of the hierarchy. At least in the signal list. There's a signal list, which I think I show, yes, right there. So this is they call it objects, but it's objects instead of signals because sometimes there's RAMs in here. You might have a RAM. So they're not all signals, but in this case, they're all signals. I have a 9-bit A, 9-bit B. Of course, you see they're X's, which means it doesn't know what they are. It doesn't know the value. There's a clock, carry out. Yeah, it actually has, I don't actually even understand this. It has X's here, right? So that's one of the states, right? But then they have strong X. Yeah, I don't know why it's strong X. I can't explain that. I don't know where it gets the strong X from. I get the strong 1. That's like if you force a signal inside the simulation environment, because that strong 1 can't be overridden if you set it with a tickle command force. Tickle is the command line language used in model sim. But strong X, I can't explain that. Okay. So, by the way, you might be wondering, what do we do with these? Well, you can drag these into your wave window. You can right-click these and force them to a value. That's what they're here for. They're there so you can do stuff to your signals. Okay, and then there's the wave window where you can write. I think I did show this last time, right, on Monday? I think I went through this example where you can right-click and say add to window, and it'll put them in the window, the wave window there. Okay. Alrighty, and then the wave window looks like that. Okay, and then there's a few commands you can use in model sim. So if you use a test bench, and I'm going to talk more about that just in a minute. Test bench is a way to write a module that tests another module, and it's more automated. So you usually don't have to do much with a test bench. You just all you do is you open a model sim and say go. That's it. And then if there's any errors, it'll probably print an error message, right? Because you can do that, right? However, sometimes you don't have time to write a test bench, or you don't want, or you're like me, you're too lazy to write a test bench because you want to do a unit test of just one little thing, and you don't want to take the time to write a whole module just to test that, right? So there is some shortcuts in model sim where you can force individual signals, like, in other words, inputs, right? Obviously, what are you forcing? You're forcing the inputs, right? And then you're looking at the corresponding outputs. That's the whole idea. So when you want to set an input, you can just use the force command. Force is a tickle command. Tickle stands for tool command language. And it's basically a way to just set a value. And you can do this through the GUI too. You don't have to type it in. You can just right-click the signal and just say force in the GUI. So there's more than one ways to do that. And then so you can force inputs, and then when you want to advance the simulation, you can just type run space and a time. And that time, the units of that time are going to be whatever units the simulation was set up to be when you started. It's usually picoseconds by default. So this will run for 100 picoseconds. And they might say, holy cow, that's a fast circuit if it's running in 100 picoseconds. Yeah, but it's irrelevant. The units are irrelevant because we are not modeling circuit delay. We're not, because circuit delay comes from capacitance and resistance in the circuit. Capacitance comes from just the fact that you have metal that sits on top of a dielectric, right? On the chip. That creates capacitance. So the longer and the fatter and the wider, the more area your wire has, the more capacitance, and the longer the wire is, the more resistance it has. And of course, transistors and active devices have capacitance and resistance, and all that contributes to delay. But because we don't know anything about that in model sim doesn't know any of the technology parameters. It just knows about the behavior, the logic behavior. So thus, there is no delay in this. So when you simulate in model sim, it's infinitely fast, right? Now, so what that means is that if you set an input, the output will change after you set that input, but with an infinitely small amount of time after you set that input. So there's an epsilon delay, basically, right? So there's all the logic delays are epsilon. Now you can actually, model sim is capable of modeling logic delay. You can actually, and I've done this before, but it's really tedious. You can actually place and route your design on the FPGA, and then you can pull data off of that compiler and backfeed it into model sim, and model sim will then start behaving like the FPGA does in terms of delays. It's kind of cool, but it's not practical. No one ever does that. Why? Because the FPGA compiler has a timing spec. Remember I told you about the timing spec, it'll tell you whether it's going to meet the minimum timing requirements. So there's no reason to ever simulate with delays in model sim if the synthesizer is going to guarantee you that it's going to meet your timing spec, right? So I don't know why they have that timing capability in model sim. It's useless, right? Because the CAD tools have timing closure built in, right? The only thing you're using model sim for is the behavior to test the functionality, not to test the performance in terms of the logic delay, okay? So the clock being 50, in this case, I'm setting up a clock to be a period of 100 with a duty cycle of 50 picoseconds. You might say, oh, that's a fast clock, but that's just a placeholder. We don't really care. Pico, nano, seconds, doesn't matter, right? So we usually just use picoseconds. Okay, so and then you can create a script, but I'll come back to this. I don't think anyone's going to use that. Okay, so then we've got Quartus. So model sim is where we simulate. Quartus is the tool that will synthesize and interacts with the physical hardware. So once you're satisfied that your behavior is correct, then it's time to bring it into Quartus, which will do two things. It'll guarantee you'll meet your timing spec, and it'll synthesize your Verilog onto the FPGA. It deploys it, and it'll make it appear. It'll basically take your logic circuit and cause it to materialize into reality. Like it'll become something tangible, a real tangible circuit. So like when you build your FPGA and you synthesize it and download on the FPGA, you have physically made a tangible CPU. You have a circuit that you've made that you can then interact with. And then after Lab 4, you'll interact with it by flipping the switches. It'll calculate the square root using your code from Lab 1, and it's going to give you the result on the 7-segment displays. Now you might say, well, yeah, but I mean, come on, we don't get to solder, plug wires in. Yeah, you don't want to do that. Trust me, that's awful. If you ever did breadboard stuff, or even did a chip layout, by the way, which is also terrible. That's when you actually you draw polygons that you send to a chip fabrication place to actually fabricate an ASIC. Yeah, it's awful. I used to spend, when I was in grad school, I used to spend months just routing the pad frame for a chip, just drawing the polygons to create the I/O pads and making sure that all the design rules are met by filling in all the empty spaces with metal stacks and all that stuff. It's putting in all the decoupling capacitors on the power supply. It's awful, right? This is much better. The fact that you can make hardware this way is awesome, right? Even though it may seem kind of untangible, it is actually creating legit hardware. Okay, so anyway, Quartus is a tool. Now, the thing is that in this class, this is not true if you take 313. Some of you took 313? No, okay. So we teach 3 classes now with these FPGA boards. This is the only class where we've automated this Quartus part for you. Because I had a really good grad student that wrote scripts. So instead of going through Quartus, all you have to do is type CSCE 611.sh compile. And it will actually compile your design through Quartus, but using the command line. So you'll never see the GUI, right? Likewise, when you want to program the FPGA, you just type CSCE 611.sh program, right? And I'll show you a demo of that. However, you might be curious how Quartus works, right? And if you are, it's nice because we also give you the Quartus project file. We just made it for you. Now you might say, well, why not just create it from scratch? Why did you give it to us? Because when you create the Quartus project file, you have to choose the FPGA part, and there's like 11 million FPGA parts. I don't know why there's so many FPGAs. There's every variation because there's all these different technologies, generations, and then each one has a different size, and then each one has a different speed grade, and then each one is in a different package. So you get this you get a combinatorial effect with all these FPGAs. So just finding the right FPGA is kind of a pain. And then you have to bring in the pin map. The pin map maps the physical pins, which is a grid, which is like an Excel spreadsheet. So there's a ball grid array on the back of the FPGA. It's a 2-dimensional grid of indium solder bumps that is pressed onto the board, placed onto the board, and then heated and melts the indium. And it's a grid, so the rows of that grid are numbers and the columns are letters. So for example, you might have a pin on there that's like B37, which is one of the pins on the backside of the FPGA. And that one was routed to one of the LEDs on the board, right? But you don't want to have to remember those names and those numbers. You just want to say LED 5, right? And so the pin mappings are what makes that sets up that correspondence. So that's something else you have to set up. And inevitably, if you guys do this manually, you'll forget to do that pin mapping. And so if you don't have a pin mapping and you synthesize your design, it will randomly connect pins from your top level design to pins on the board. So it'll glitch and freak out. The board will do this weird glitchy, flashy thing. If so you don't want that. So we just kind of set it up for you. But anyway, if you do want to launch Quartus, you just type Quartus. It brings up this splash screen. You can turn that off, and then you'll see something that looks like that. And you can actually open up. You can say File, Open Project, and open the project file that we give you if you want to see it. And you can compile from here. And there's some other things you can do from here that we don't support in the script. One of which is Signal Tap, which allows you to probe signals on the FPGA with a virtual logic analyzer, meaning that you can actually see what's going on in the FPGA. Now you might say, well, wait a minute, why would I ever do that if I can simulate it? Because sometimes when you simulate your design, it works. Then you put it on the FPGA and it doesn't work anymore. And it's like, nah, well then what do I do now? Well, there's nothing you can do. The only thing you can do at that point is be able to use this logic analyzer to see, or you could check log files. Sometimes the log files will say, oh, I optimized your design out. Sometimes your design gets optimized out. Like this compiler might think that your design is irrelevant because you didn't connect it to pins. That happens sometimes, right? Like if you don't connect your design to pins on the FPGA, the compiler will say, well, what's the point? I mean, I can put this circuit on the FPGA, but there's no way to access it from the outside world, so I'll just delete it. And that's exactly what it does. So you'll compile it, and it'll say 0 LUTs. And you're like, what do you mean 0 LUTs? I put a whole CPU on there. Yeah, well, it optimized it out, right? So sometimes that happens. But other times what happens is you'll have a latch in your design. You'll write code that implies a latch as opposed to a flip-flop. Latch is a level-sensitive memory element. Hopefully you guys talked about that in 2.11. And latches, sometimes you can't put latches on an FPGA because there's no primitives for latches. There's only primitives for flip-flops, edge levels. So sometimes stuff like that happens, right? You'll have some behavior in your code that is not implementable using the primitive circuits that are on the FPGA, and therefore it won't work. And sometimes you'll get an error, but you might miss the error, or maybe it'll be a warning. So that's an example. In that case, you may want to go in and use Signal Tap. Alrighty, that's the pin mappings. Okay, so let's move on to one final topic in terms of Verilog syntax, and then I'm going to talk about the lab, and you guys should be good to go. Okay, so the final thing. Okay, so I mentioned two kinds of two kinds of Verilog. There's structural Verilog, which is just instance this, connect this, right? Instance these things and wire them this way, right? That's basically just creating a schematic. Then you've got behavioral, which is logic behavior. It's like the Boolean logic stuff, right? And all I showed you for that was the assign statement, the continuous assign statement. It just assigns a value. There's a couple problems with the assign statement. Number one, there's no way to have an assign statement that has memory. In other words, if you use an assign statement, it can only be combinational logic, meaning that there's no memory, right? There's no way to store something in an assign statement, to grab it and to hold it, to store it in a memory, right? For that, you have to use this always construct, right? The other problem with an assign is it's basically one line of code. I mean, you can put line breaks in there. So you can create this really big, long, nested ternary statement. But essentially, an assign statement is one statement. There's just one semicolon at the end, right? So everything you put in an assign statement has to be essentially in one line of code, right? From the standpoint of, the semicolon, one line of code. So if you want to do some complex, like if you want to put a big truth table in there, you don't want to necessarily do it with an assign statement. You probably want to use something with semantics that are a little bit more familiar, like if statements and case statements, right? And so for that, you can use an always. But here's where things get a little confusing, though. So an always statement is basically a block of code that you can then use if statements, loops, case statements, and you can put memory into. So you can create sequential logic or combinational logic with an always statement. The problem is sometimes it's easy to mess up because, for example, if you're making a combinational logic in an always, you have to be sure that you assign all of the possible outputs of that always statement and every possible control path through it. Otherwise, you'll end up implying memory when you didn't mean to, right? In other words, I'll talk more about that in a minute, but basically, sometimes you want to do combinational logic and you might accidentally make sequential logic, right? It's a little bit, you can get yourself in trouble. But another nice thing about always is you can assign multiple outputs. And the other thing too is, one final thing, the assign is creating a logic circuit. So remember how I mentioned that you can only drive an output with one logic circuit. You can only drive one signal. Anything you drive, any output you set in an always is owned by that always statement. So that's the logic circuit that drives it, right? And so essentially what an always statement is you could think of it as an assign statement, but just more complex, that has multiple lines of code in it. Does it make sense? Okay, so like for example, you'll use an always statement to create the control unit for your CPU because the control unit is a big giant nested if then else statement, right? And so it's more appropriate to use an assign, an always for that, okay? Okay, so now one thing that we have in SystemVerilog that helps a little bit is SystemVerilog introduced variations of the always. So we have always comb, and we have always underscore FF, flip-flop, and there's also a couple other ones. But if you put always comb, you just say always comb, and then you have begin and end, or if you have multiple statements, begin and end is how you make a block as opposed to the curly braces. That will basically cause an error if you accidentally imply sequential logic, right? Likewise, always FF will give you an error if you accidentally imply a latch as opposed to a flip-flop, right? However, there's always just the always, which always does anything, but you can get yourself into trouble if you use always, because by adding these little suffixes, it gives you some protection. It allows you to tell the compiler exactly what you're trying to do in that always, okay? So I know that's a little vague, so let me show some examples here. So for example, I can have an assign statement like this that creates a mux. And the mux basically just says, I want to assign out1 to be foo if select is equal to 1, and I want it to be bar if select is equal to 0, right? So I use a trinary statement. However, I can do the same thing with an always comb, but because I'm using an always comb, I can use an if statement in there instead. So I can say always comb begin, and then I have an end, and I can say if select, then out1 equals foo, else out1 equals bar. So now I can use the familiar if then else statement in here, right? The problem is you have to be careful that regardless of what happens in this if, I always assign out1, no matter what the outcome is. Because if you have a pathway through here that doesn't assign out1, then obviously out1 is going to have memory. It's going to have to say, well, the always executed, but you didn't assign out1, so I'm assuming I'll have to hold on to the old version, the old value of out1, which is okay, but then I need memory, and then that's sequential logic. So you have to be careful with that. But luckily, if you made that mistake, and as long as you use always comb, then the compiler would have caught that. Okay? Now, the question is, what do you mean by run? Okay, because now you've got an if statement. You have an if statement, and you said in the last lecture that Verilog has concurrent semantics, meaning that every line of code in Verilog runs concurrently, and so you can mix the order up of the code and it makes no difference. Well, obviously that can't be true if you're talking about an if statement, because if statements do have an ordering associated with them, right? Well, that's because what's happening here is that the always comb is getting synthesized into a logic circuit, and it will activate whenever any signal that's treated like an input changes state. It will activate it like an always statement. But when it activates, it executes the body of the always as an atomic operation, as a circuit, right? So even though you could think of an if statement as having sequential semantics, it walks through one line at a time, it's the overall end-to-end behavior is kind of combined into a digital logic circuit and it's activated whenever the inputs change. Now in this case, what are the inputs? Well, select. Select is treated as an input, so it's an input. And foo and bar are inputs here, right? So I basically have 3 inputs. If any of these 3 inputs changes state, that will cause an event to trigger, which will update out1 immediately. I mean, just after the logic delay. And the way that out1 is updated is basically behaves as though I'd run this sequentially, but it's still not sequential. It's just the sequentiality inside the always defines the behavior. You guys, I know that's kind of esoteric, but it's basically a way, it's just a way to make a complex assign statement, essentially. So this code and this code are identical. These will generate identical hardware. So here's another way you could write it. You can say, this gets even more confusing. So I can assign a default output of out1, I can set it to bar. But then if select equals 1, and notice I forgot to put 1 apostrophe B1. I screwed that up. Remember I said you're supposed to put the with on here and I didn't do it. I said this is bad, I need to fix. Actually, this wasn't my code. I think I got this from the textbook. To be fair to me, I think the textbook screwed this up. It should say, I mean this will still work. The compiler will figure it out. But this should say if select equals 1 apostrophe B1, right? Meaning 1 bit in binary 1. But anyway, if select equals 1, I want to overwrite out1 and select it to foo. Now you might say, wait a minute, you just double drove out1. No, because out1 was assigned twice, but within the same always, it's okay. However, you're not going to see the hardware change its mind here. It's not going to set out1 to bar and then change it to foo. It's only going to apply the last assignment, right? So basically, this is equivalent to an if then else. And the reason I wrote it this way is so I was guaranteed that I would always assign the output to something every time this thing activated, right? So say select change states, it activates this and I'm guaranteed that it'll be overwritten. But you're never going to see the hardware switch from bar to foo. It'll just go to foo because whatever you assign last is the thing that it'll commit to when it activates that always, right? So this is where the sequential versus the concurrent semantics gets really kind of confusing because it's like normally with a programming language, if you did this, you would see out1 get bar and then you would see then it get foo if select was 1. But that's not what happens in Verilog. It just gets set to foo if select is 1. Otherwise it gets set to bar. Okay? Okay. All right, so the last thing I want to mention is this because this is something you may want to use for lab 1. So there is a in and always. Oh, there's actually 2 more things. The always you can have. Actually, no, this isn't. Sorry, scratch that. This is just setting multiple outputs in always com. That's not exciting. This is what I'm going to show. The case statement. So there is a case statement, which is in other words a switch statement, right? In Java and C, it's called a switch statement. In Verilog, it's called a case statement. But basically, it allows you to put an if then else. So this is a 7-segment decoder where I basically, the syntax here is essentially case is the input. These are the different cases. Use colons, there's a default. And notice here, I actually do have the proper syntax 4 apostrophe D4. So what I'm saying here is if data is 4, then I'm going to set segments to this 7-bit value, right? So this is similar to what you guys are going to do in lab 2. Notice that there's a couple important differences. The first difference is this 7-segment decoder only goes from 0 to 9, and in lab 2 you have to go from 0 to F, right? You want to do a hexadecimal 7-segment decoder. That's 1. 2, if you look at the manual for the FPGA, which I linked on Dropbox, the 7-segment decoders on here are ordered from least significant to most significant, whereas these bits are actually reversed, right? So in other words, the A input on the 7-segment decoder is the top segment, right? And it's the most significant bit here, whereas on these FPGAs, it's the least significant. So you have to kind of reverse the order. And finally, the 7-segment displays on this board are active low, which means you set the segments to 0 to turn them on and 1 to turn them off. And this assumes active high. So, but you know, making those, you can make those changes, and so you can use this as a starting point, but you're going to have to make a few changes on these boards. Okay? And I'm assuming you guys are cool with 7-segment displays. You guys talk about those in 2.11? Yeah, so basically just, you're forming numbers and letters from 7 segments. Okay, and then, so I'm going to kind of fast because most of this is pretty basic stuff. There's also a case Z variant where you can put don't cares in the input, but I'm sure you guys can figure that out. Okay, and the last thing is sequential logic. So, so I'm not going to have time to, I was going to do a demo of this today. I just ran out of time though, but if you use the always FF, okay, you can make a sequential logic that's clocked. The idea is that you have to specify a sensitivity list, which is something you don't need for always com. You can say always underscore FF at, and then in the parentheses, you could tell it under what conditions should this trigger, okay? In this case, I'm going to use pos edge clock, which means the rising edge of the clock. There's also a neg edge clock, and you can add other things in here, separating them with commas, right? But in this case, this says always FF, so instead of this thing triggering when any of the inputs change, it only triggers when things in the sensitivity list change state or happen. So in this case, this creates a D flip-flop where the output Q is going to get D on the positive edge of the clock. This is very common. You'll have a lot of these in your CPU design because this is how that you're going to make your pipeline registers. This is how you carry data from one cycle into the next cycle in time, right? So for example, when you do lab 4, we're going to have a branch instruction. The branch instruction has to, if you take the branch, it has to automatically stall the next instruction, right? So you execute the branch. If it's taken, you have to flush out the next instruction that'll be executing in the next clock cycle. Well, how do you do that? Well, you just use this. You say you have a stall signal that's generated combinationally in the control unit called stall fetch. And you assign that to stall execute in this statement. So if you set stall fetch now, then that signal will propagate to the next cycle, and then in the one cycle into the future, it will be called stall execute, at which point the control unit will have communicated a signal forward in time. It'll send a message to the future, essentially one cycle into the future, saying, when you get the next, like note to self, when you get the next instruction, kill it. Because this is a branch. I took the branch, but it's too late. If I'm executing the branch, I'm already fetching the next instruction. So it's too late to do anything about it now. So in the future, kill that instruction when it comes into the execute stage. So this is the way that you would create that. If you don't do that, then you end up with a combinatorial loop where the control unit says stall, and so you stall it immediately, and the branch turns into a stall. And you're like, oh, I don't need to stall. Don't stall. And then it turns back into a branch. And you say, oh, it's a branch. I need to stall. Stall turns back into a stall. And you get into this combinatorial loop, which if that happens, ModelSim freezes. It doesn't crash. It literally freezes. It goes into a combinatorial loop, and it generates an infinite series of events that happen in the Verilog code. And there's no way to get out of it. And even worse, there's no way to find out where the combinatorial loop is in your design. If that happens, you literally have to start deleting parts of your design randomly and rerunning to find out if you randomly selected the part with the combinatorial loop, because ModelSim will not tell you where those loops are. All it knows is it just freezes up, right? But having these flip-flops in here allows you to delay signals into one cycle into the future. Make sense? Okay, so I'm just about out of time, I think, right? Yeah, so Lab 2 is posted. There's a lab sheet and there's a project skeleton. You download the project skeleton. We didn't give you one for the last lab. You just did it in RARS and submitted the RARS code. Now there's a project skeleton. So that skeleton includes the project file and the scripts that you're going to use and the pin mappings. So you just download the skeleton, and there's also a starting point in there. We give you a little wrapper where you can start your design. And so check that out. It's described in the lab sheet. And if you have any questions, we'll be here to help you in lab on next week. Okay? Okay, any questions? Yes?
I on Monday you were talking about how the quiz on Friday was contingent on finishing.
Yes, yeah, and I got far enough. Yeah,
Oh,
quiz.
do it by credit?
Yes, yeah. Make sure you take the quiz. Thank you. Yeah, make sure you take the quiz. The quiz covers RISC-V assembly and Verilog. And I think there's 10 questions. They're pretty simple. Yeah, and I covered everything I need to cover for that. Okay, and we'll have another quiz next week. It'll also cover Verilog. It'll be a little harder. Okay, thank you.